Today we are going to discuss a small topic in the subject computer aided design and analysis. Already we are discussing fifth module and today's topic is global stiffness matrix. Along with that we are going to discuss a problem regarding stiffness matrix. We have already studied steps in FEM and in previous presentations we have completed discretization, selection and numbering of nodes and elements, selection of nodal displacement function, also shape function, that is known as shape function, forming element stiffness matrix, and today we are going to study assembling of global stiffness matrix and applying boundary conditions and solving simultaneous equations. First of all, we start with assembly of global equations. For that, we select a vertically hanging bar as shown in the figure. That bar is discretized as element 1, 2, 3 and 4 with nodes 1, 2, 3, 4 and 5. Element 1 is with n conditions, node 1 and 2, that is element 1 having two nodes 1 and 2, and element 2 having two nodes 2 and 3, and element 3 having two nodes node 3 and node 4, and element 4 having two nodes element 4 having two nodes node 4 and node 5. And finite element equation is given as F is equal to K into U, which is discussed in previous presentation. Now we are going to form element stiffness matrix for each element. We have derived element stiffness matrix in the previous presentation and today we are discussing how that is assembled. First, select element 1 which having nodes 1 and 2, and nodal force will be F1 and F2, and element stiffness matrix will be A1 E divided by L1 into matrix 1 minus 1 minus 1 1, which is known as element stiffness matrix, and matrix U1 and U2 is known as nodal displacement, that is U1 at node 1 and U2 at node 2. Similarly for element 2, which is having nodes 2 and 3. For element 2, the n conditions will be node 2 and node 3. So nodal forces will be F2 and F3, and area of cross section of element 2 is A2, and smallest e, L2 is the length of element 2, and matrix will be 1 minus 1 minus 1 1, similar to earlier one, and nodal displacement will be U2 at node 2 and U3 at node 3. Similarly for element 3 we can have the equation, and for element 4 also we can have the equation, and there is a small correction, that is element 4 having node 4 and 5 as n condition. You can see the figure, but it's wrongly marked in the presentation. Now we are going to assemble all the matrix. For that, first, for easy calculation we assume area as constant and length of each slab as constant, that is A1 is equal to A2 is equal to A3 equal to A4 equal to A, and L1 equal to L2 equal to L3 equal to L4 equal to L, that is for elements all areas are constant or length are constant. And assembling the equation, we can find nodal force F1, F2, F3, F4, F5 as combination of global stiffness matrix and nodal displacement. Nodal displacements are U1, U2, U3, U4 and U5, and global stiffness matrix is found by adding element stiffness matrix at each element together, that is 1 minus 1 minus 1 1 is the stiffness matrix at element 1. Similarly 1 minus 1 minus 1 1 will be at element 2, 1 minus 1 minus 1 1 at element 3, 1 minus 1 minus 1 1 at element 4, and from all equation E, A and L are taken outside since we assume it as constant. Normal problem, that will not be constant, that should be inside the matrix. When finally calculating, we will get the equation as element stiffness matrix A into E into L So E divided by L into 1 minus 1 minus 1 2 minus 1 minus 1 2 minus 1 minus 1 2 minus 1 minus 1 and 1. Now for a clarification of this equation, this derivation, we need to do a calculation. For that we select a 2 element with 3 knot as shown in the figure. I will read the problem, that is, consider a bar as shown in the figure. An axial load of 200 kN is applied at point P. Actually P is not marked in the figure. P is similar to node 2, that's why we can take it as node 2. P is as node 2. Take A1 is equal to 2400 mm square, Young's modulus E1 equal to 70 into 10 raised to 9 Newton per meter square, A2 is equal to 600 mm square, E2 is equal to 200 into 10 raised to 9 Newton per meter square, and calculate the following. First one is nodal displacement at point P, that is node 2. U2 should be found. Stress in each material and reaction force. And length of elements are given as L1 is equal to 300 mm, L2 is equal to 400 mm. Also, node 1 and node 3 are fixed points. Now we will write the given data as in the slide. A1 is the area of cross section of element 1 and that is 2400 mm square. E1 is the Young's modulus of element 1, that will be 70 into 10 raised to 9 Newton per meter square, but that's in meter, we need to convert it into mm since all other units are in mm. So that will be 70 into 10 raised to 3 Newton per mm square. L1 is the length of element 1, that is 300 mm, and for element 2, A2 is equal to 600 mm square, E2 is equal to 200 into 10 raised to 3 Newton per mm square, L2 is equal to 400 mm, and point load P is equal to 200 kilonewton, that is at node 2 force is applied. Force applied is 200 kilonewton. Now we will form element stiffness matrix or finite element equation for each element. First we will take element 1. For that we have the equation. Rearrange the equation, we will get A1 E1 L1 into matrix 1 minus 1 minus 1 1 into U1 U2 equal to F1 F2. Substituting the values, we will get 2400 into 70 into 10 raised to 3 divided by 300 into matrix 1 minus 1 minus 1 1 into matrix U1 U2 equal to matrix F1 F2. Finally, we can write it as 1 into 10 raised to 5 into matrix 5.6 minus 5.6 minus 5.6 5.6 into matrix U1 U2 is equal to matrix F1 F2. For element 2, that is between node 2 and 3, the same equation can be written, and applying or substituting the values, that will be 600 into 10 raised 200 600 into 200 into 10 raised to 3 divided by 400 into matrix 1 minus 1 minus 1 1 and matrix U2 U3 is equal to F2 F3, and final value will be 1 into 10 raised to 5 matrix 3 minus 3 minus 3 3 into U2 U3 is equal to matrix F2 F3. Assembling equation 1 and 2, equations at element 1 and 2, we will get 1 into 10 raised to 5 into, you can see this is for element 1 and this is for element 2, that is for element 1 5.6 minus 5.6 minus 5.6 5.6, and element 2 3 minus 3 minus 3 3. So middle value will be become 8.6. This will be the final finite element equation. Now we will apply boundary condition. For that we need to refer the figure as given earlier, that is from the figure node 1 and 3 are fixed as I mentioned on that condition. So for a fixed position there will not be any deflection, so we can select U1 equal to U3 equal to 0. So there will be only nodal displacement at node 2. And in the problem given that a load of 200 km acting at node 2, that is F2 equal to 200 into 10 raised to 3 Newton, and at point 1 and 3 there is no force is applied as given, and taking self weight as negligible, we can write the equation as 1 into 10 raised to 5 into matrix 5 minus 5.6 minus 5.6 8.6 minus 3 3 into matrix u1 and u3 are 0, so 0 u2 0 equal to f1 and f3 are 0, so 0 200 into 10 raised to 3 and 0. And when multiplying and solving, we can write the equation as 1 into 10 raised to 5 into 8.6 into u2 equal to 200 into 10 raised to 3. We need to do matrix multiplication, and this method is known to all. So while doing, we will get only one equation since all other data are. You can see that u1 and f1 are 0 and u3 and f3 are 0. So you will get only one equation, that is 1 into 10 raised to 5 into 8.6 into u2 equal to 200 into 10 raised to 3. By solving that, we will get displacement at node 2 as u2 equal to 0.2325 mm. Now we need to find stress at each element. For a finite element analysis, stress is given as sigma equal to x modulus E into du by dx, where u is the deflection at each node and x is the variation in length from initial node to final node. So for element 1, the equation can be written as sigma 1 equal to Young's modulus E1 into final deflection, that is u2 minus u1 divided by L1. L1 is the length, that is the distance between node 1 and 2. So by substituting value, we will find stress as 54.25 Newton per mm square. Since the value is positive, this stress will be tensile stress. And selecting element 2, same equation will be applied, but the boundary condition will be vary. u3 minus u2 will be the difference in deflection, and L2 will be the distance between node 2 and 3. So substituting value, we can get stress as minus 116.25 Newton per mm square. That is, the values are negative, means that will be compressive stress. So in this case, there are two stresses. For element 1, that is tensile stress, and element 2, that will be compressive stress. Now we need to find reaction force. For that, we need to learn a new equation, that is R is equal to K into U minus F. The difference between K into U, that will be the multiplier factor minus F. And when substituting all the available value, we will get this equation. And we need to substitute all boundary conditions in this equation, that is u1 is equal to 0, u2 is equal to 0, f1 is equal to 0, f3 is equal to 0, and u2 is equal to 0.2325 mm, and f2 is equal to 200 into 10 raised to 3 Newton. Applying that, we will get this equation as such, and when multiplying this equation, we will get equation as like this. And when we are dividing initial value, when we are subtracting this one from this one, we will get the reactive force at each element. so each node, sorry. So the final value will be reaction force at node 1 will be minus 1.302 into 10 raised to 5 Newton, and reaction force at node 2 will be 0. Reaction force at node 3 will be minus 0.6975 into 10 raised to 5 Newton. This will be the format of solving a finite element problem. Similarly, there will be a lot of problems available in the Moodle. So please check that also. Thank you.